So let's talk about product rule. What do I mean when I say product rule? Product rule talks about taking the derivative of the product of two functions. So let's say I have a function f of x and I multiply it by g of x and I want to find the derivative of that whole thing. Well, one might guess that it would be the derivative of each of the pieces, and I would write that as d dx of f of x times the derivative of the second piece. Now this is my conjecture. I'm just asking, how would this work out if this were the case? We'll see actually in a moment that this is not how it works. But let's operate under this assumption by looking at an example. So let's say I have a function f of x, which is 2x, and a function g of x, which is x cubed. And I want to know what is the derivative of the product of these two functions. And I'm trying to make this focus a little better. There we go. So that's asking us, what's the derivative of 2x times x cubed? And the reason why I chose these functions is because we can always verify this by looking at the derivative directly. So if I used my fake product rule, what would I get? The derivative of my f function using power rule, this is x to the 1. So when the 1 comes down, we see that the derivative of this is just 2. It's a linear function, 2x, and the slope is 2. That's another way to think about it. So we know that we get a 2 from the first function. And what's the derivative of the second function? I'm going to use power rule, and I know that the 3 drops down, and I subtract 1 from the exponent. So that would be 2 times 3x squared, which is equal to 6x squared. Now let's verify this by knowing, or by taking the product of this first and then taking the derivative. So if I take the product of these two functions first, I end up with 2x to the 4th. And let's take the derivative of 2x to the 4th. We can use power rule again. The 4 drops down, and so I end up with 8 as my coefficient. 4 times 2 is 8, times x cubed. Notice that these two things don't match. So that tells me that just taking the product of the derivatives is not going to be right. So let's go back up to this and say, no, we can't just take the product of the derivatives. That's why we have a rule. It's called product rule. And let's explore this. I'm going to take a step into theory, but I actually think that this is a really helpful way for visualizing why the product rule works the way that it works. So we're going to go back to the limit definition of derivative. Recall that typically when we talk about the limit definition of derivative, we don't have two functions here. We would just have f of x plus h minus f of x all divided by h. But because we're talking about the product, we have all of these pieces here. And because it's a product, I'm going to use an area model to be able to visualize the product of these two functions. Just like how you can represent 2 times 3 as the area of some rectangle that's 2 in length and 3 in height, we're going to do the same thing in this case. And for this rectangle, I'm going to break it up into pieces. So along this vertical axis, I'm going to say that this length right here is represented by f of x. And then the outer larger length, maybe this is the smaller length, the outer larger length is going to be represented by f of x plus h. Similarly, this smaller length in here is going to be my g of x, and the longer length around the outside is my g of x plus h. Now, why is this helpful? Let's look at the numerator of this limit and see how this numerator lines up with our picture down here. Oops, there we go, our picture down here. So the whole thing, f of x plus h times g of x plus h, that's going to be the area of this entire rectangle, because it's the area of this entire length times this entire width. But then I'm subtracting out this inner rectangle, the inner rectangle given by this smaller length and this smaller width. So that means that what's left over when I subtract that out, all that's left is this little border part of the rectangle. That's what the numerator up here is representing. And intuitively, that sort of makes sense, that we're asking sort of how much of this changing. And when you think about this change, the change is going to be both in the x direction, well, in this f of x function and the g of x function. And so this little piece, as h goes to 0, this little piece is going to shrink in as h gets smaller and smaller. And the limit is looking at the ratio of those two things. Obviously, when h is 0, this is 0, and that doesn't make sense. But that was true before when we were looking at just the limit of a function f. So let's rewrite the area of this piece in a way that's going to be helpful for computing our limit. So I'm going to break it up into two chunks. Let's look at this upper green chunk as one piece and write the area of that green chunk. And then, so what is the length of this rectangle is g of x plus h. And the height here of this rectangle is f of x plus h minus f of x. It's the difference between the larger side and the smaller side. So that's f of x plus h minus f of x. And then I also have to add on the area of this piece over here. So how are we going to represent this blue area? So this blue area has a height given by f of x, and it has a width given by g of x plus h minus g of x. Again, this is just a different way to be able to write the numerator in our limit. And why is this helpful? When I take the limit and let my h go to 0 and divide this thing by h, some nice things happen. Notice that we see exactly this piece right in here is, as h approaches 0, this is our definition of derivative of f. And as h goes to 0, this piece is our definition of the derivative of g. And so that means that I'll write out one more step. Limit as h approaches 0. I can separate these fractions. I get g of x plus h times f of x plus h minus f of x all over h. And then I have this limit over here, f of x times g of x plus h minus g of x all over h. And like I said, when we compute this limit, as h goes to 0, this function here is just going to end up being g of x. And this piece right here is the derivative of f prime of x. Similarly, as I look at the next chunk, this just becomes f of x. H going to 0 doesn't affect it. And this chunk right here becomes g prime of x. So what did we just find? We found that the derivative, oh, you missed all of that, I apologize. We found that the derivative is going to be one of the functions times the derivative of the other, plus the other function times the derivative of the first. And let's look why that makes sense visually. Visually, we can think of this as sort of our change in f and our change in g. And so if I want to estimate the area of each of these pieces, the area of this is going to be the length of g times my change in f. So the length of g is right here, and my change in f, when I take it as the ratio as h goes to 0, becomes my derivative. Just like over here, this length is f, and this change is my derivative of g. You might be asking about this little rectangle here. It turns out that went to 0 as our h goes to 0, so we don't have to worry about the corner piece. But this is my way of remembering how product rule works, that it's my first function times the derivative of the second function, which gives me this blue area, plus my second function times the derivative of the first function, which gives me my green area. Let's look at that formally. So here is product rule formally written, and I have it written and using both types of notation because I want us to be comfortable using both of these notations, the dx notation as well as our prime notation. So this is saying the derivative of the product of two functions is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. And notice I could have gone in either order because addition is commutative. It doesn't matter whether I take this piece first or that piece first. And this is the definition rewritten just using our prime notation. So f times g prime is going to be f times g prime plus g times f prime. So let's go back to the original example that we looked at and see what happens when we compute our derivative using product rule. So in the example at the start of this section, we had f of x equal to 2x and g of x equal to x cubed, and we want to know what is the derivative of 2x times x cubed. Using our product rule, that's going to be the first function times the derivative of the second function. Our first function is 2x. The derivative of our second function, we have to use power rule, so that becomes 3x squared. And then I'm going to add the second function times the derivative of the first function. Our second function in this case is our x cubed function times the derivative of the first function. This is just our linear function with slope 2. So I end up with 2. Let's simplify this a little bit. 2 times 3 is 6, and x times x squared gives me an x cubed, so I have 6x cubed here. And then over here I have 2 more x cubed. So altogether I end up with 8x cubed. And let's go back. Well, where did I put that paper? And that actually aligns perfectly with exactly what we said that it was going to be when we did our product rule the first time. So remember when we did our work before, if you multiply them together first and then take the derivative, we get 8x cubed. This one was the wrong answer. 8x cubed is the right answer. In some ways, this is sort of an artificial example because it's probably easier just to multiply these first and then take the derivative. But for other examples that we'll see later on, it'll be much easier to be able to take the product sometimes using the product rule rather than having to do messy multiplication if these two things are really messy.